Okay, I think we'll get started. If you're coming from the GNL project, then I encourage you to look at the introductory video for this playlist to make sure this is the right series for you. Today we're going to talk about ropes and pulleys. And so we've talked about, we mentioned a rope before in the context of our cataloging of forces and this idea of tension. And rope is what mediates that tension force. So the force is tension and it's directed along the rope. So if we're pulling a box along the floor with a rope, then there's a tension in that rope and that is carrying that force that we're applying to the box. So we could imagine ourselves with a rope tied to the wall and us pulling with 100 newtons of force. Well, then that rope is pulling back on us with 100 newtons of force. It's a little easier to see, I think, if you imagine with your friend, you've got one end of the rope, your friend has the other end of the rope, and you're pulling and you're stationary. So you're not pulling your friend or your friend's not pulling you, but you're pulling tight, kind of stuck, locked in place. Then there's a tension there. If you're pulling with 100 newtons, then your friend would have to be pulling with 100 newtons as well. And here's an important point. The tension in the rope then is not 200 newtons. It's 100 newtons throughout, and here the tension, you're supplying a tension of 100, a force of 100 newtons here to the rope. The rope is carrying that 100 newtons to pull your friend in that direction. In order for your friend to counter, he or she is pulling in the opposite direction with an equal force. So with 100 newtons, and so that is being mediated down here, pulling on you with 100 newtons of force. So these are action-reaction pairing. If we were to draw a free body diagram for you, you would be experiencing a tension force being pulled in this direction, or the force from the tension of the rope, and then a free body diagram for your friend, the tension would be in the other direction. Okay, let's imagine now we're trying to lift a weight, right? And we could tie a rope to it and we could lift it up like this, right? We could pull it up off the ground. That'd be perfectly fine. We would be supplying a tension force and the weight would hang there with a weight force. If we supply more tension force than the weight force so if we apply a force, it's mediated by the rope that's tied to the weight. That has a tension force upward. If that exceeds the weight force, then we'll pull the weight upward. We'll start to accelerate the weight upward. If the weight is heavier, then we'll get pulled downward, right? Because we don't have enough counter tension to pull that weight up. And if we're holding just with exactly the same amount of tension, then the weight will just hang there. We've seen some problems where we had hanging weights before when we were talking about equilibrium. Well, we could imagine, what's great about a rope is the rope can bend. So we could hang a pipe from the ceiling, right? We could string the rope over a pipe and we could use our body weight then to pull up. It might be easier for us to pull down in order to lift the weight up. The trouble with throwing the rope over a pipe is that the rope has to slide across the pipe. And there can be a lot of friction there, meaning we'd have to overcome a friction force in addition to the weight force. So it might be counterproductive to throw it over a pipe. Even though we could use our body weight, it still might be harder to lift the weight off the ground than just simply lifting it. However, if we replace the pipe with a wheel and string the rope over the wheel, then we have what's called a pulley. And the wheel can rotate relatively freely. In fact, to a good approximation, it can rotate without friction. So if it's well oiled, it's got good ball bearings, it can rotate very, very friction free almost. So then we're not fighting any friction. We can use our body weight to pull down, and it might be easier to lift the weight up. Another example might be if we need to pull something up from the ground or from a hole or something, and we're able to establish a pulley system. We could have a tied to the back of a car or have a winch on a machine, and we could pull horizontally to lift a weight vertically. So the pulley is a way to redirect the force, to change the direction of the force. So if we're pulling here with 100 newtons and we have a pulley that will be pulling up with 100 newtons. It's a nice way to redirect our force. Okay, let's look at a few examples here now, and we're going to look at examples where we're out of balance. So we're not in equilibrium, and we'll get some acceleration because we'll have a net force. And those are a little bit more complicated than the equilibrium problems. Okay, so kind of related to what I set up here, let's set up a system where we have one mass here that's free to slide along a frictionless table. We've got a pulley and a mass down here. So kind of like I was talking about here, we have a horizontal tension is being converted into a vertical tension and vice versa. Well, as I mentioned up here, the tension is the same on both ends of the rope. So the tension here, the magnitude of the tension on this is equal to the magnitude of the tension there. We can't really say they're in equal and opposite directions, but they're in opposite directions of the way the rope is going. So the tension from due to this guy is this weight is trying to pull this mass this way, and this mass is trying to hold this mass from moving. Okay, so let's imagine an example here where mass is 1.5, mass 1 is 1.5, and mass 2 is 2.5 kilograms. So this wouldn't have to be bigger. The system will still want to move this way because this is frictionless. The system will want to move downward, and it'll accelerate downward. Oh, actually, no, sorry, not frictionless. Let's add a little friction there. So let's see how this will behave if we just let this drop. So we're actually going to have friction included here. So let's draw the free body diagram for mass 1. So we know we're moving downward like this. We're accelerating downward. So our weight force and our normal force exactly cancel here, as we've seen many times. Our friction force, it's kinetic friction, is opposing motion. So this goes down, this guy wants to slide this way, so we have a friction force opposing motion that way, but it's not sufficient to overcome or to hold back the tension. So the tension magnitude in the opposite direction of friction is greater. So this mass is going to accelerate this way. Free body diagram for this guy is a little simpler. It's not touching the table or anything, so it just has the weight and it has the tension. It's dropping, it's accelerating downwards, so therefore the weight vector must be longer than the tension vector, higher magnitude than the tension vector. And then we have this established relationship that the amplitude or the magnitude of the tension is the same, and we'll just call that capital T. So let's first turn our attention to mass 2. The net force is simply going to be the tension minus mg. Okay? And in this case, mg is going to be bigger than T, and so we're going to have a negative net force, so we'll be going downward. And then by the second law, we also know that the net force is ma, F equals ma. So we have the net force based on our free body diagram, and then we have second law. So that's how we're going to bring things together. Equivalently, let's look at now, let's turn our attention to mass 1. So in mass 1, we need to figure out this friction. Okay, we know the weight and the normal force are going to cancel each other because the normal force always just cancels that, goes the opposite direction of that weight. So the normal force is going to be mg. So we can plug in our numbers and we get 14.7 newtons as our normal force. Because we have friction, we have a friction coefficient here, kinetic friction coefficient. That is going to give us our total kinetic friction. So we're seeing 2.9 opposing motion, so that way to the left is our friction. So our net force here is T minus friction. So just like the net force here was T minus mg, here it's T minus the friction. But in this case, T is bigger than the friction. Okay. We don't know what T is yet, so we have to just leave it as T, but we can plug in our 2.9 here for the friction. And then by second law again, we have F equals ma as well. Now, here's the key concept here. These guys are stuck together by this string, or by this rope. So they move together. One can't be accelerating while the other isn't, because we're taking this to be an ideal rope where it doesn't stretch, it doesn't break. So these guys have to move together. So if this goes down, this goes over. If this goes down, this goes over together like that. So the magnitude of the acceleration has to be equal. The direction is different. M2 is going down, M1 is going this way, but the magnitude is the same of the acceleration. So then we can combine, for both cases, we can combine the second law expression with the free body diagram expression. So for mass 1, we get this, and for mass 2, we get this. And so we have now set up two equations, two unknowns. So back to high school algebra again, two equations, two unknowns. I don't think I'll go through that, walk through that. You can check my algebra here, see if it's correct or not. But I got 11 newtons and 5.4 meters per second squared. Okay, and all I did here was two equations, two unknowns. Okay, so see if I made a mistake there or if you agree with that. All right, let's look at a very common situation, the situation I mentioned earlier where we have a loop, a pulley stuck to the ceiling, and we're going up or down with a weight. So we're going to represent that this way. We're going to take M1 and M2, and without, we're still general if we say let's always assume M1 is less than M2. If it's the other way, you can always just redraw your picture so it's flipped around. So we can always say, or relabel what's M1 and M2. So let's always make M1 less than M2 in this case. So what's going to happen? Well, if M2 is heavier than M1, M2 is going to drop and M1 is going to go up, and they're going to do so together. So however fast M2 accelerates towards the ground, M1 is going to accelerate towards the ceiling. It's always going to be like this. So we have this observation, and thus the accelerations will be equal in magnitude and opposite in direction. So we can write that as a vector here now. A1 equals minus A2, and so we'll just define that to be A. So when we see A1, we'll put it in with A. When we see A2, we'll put in minus A. And then our tensions have to be equal because we've seen that the rope has equal tension on either side, and we'll call that T. Notice this is not an equilibrium. So it's not a hanging weight from a ceiling and rope like we've seen before. So the tension here does not equal the weight. We don't know what the tension is. Okay, so very similar to what we had over here, we've got the free body diagram for one, and then we have the second law. And likewise, free body diagram for two, and the second law here. So we have two equations now, one for each mass. They're linked because A is the same for both of these. Notice here, it's positive here and negative here because the acceleration of mass 1 is upward and the acceleration of mass 2 is downward. So be careful with that. Let's solve each of these for t. So this becomes this, and this equation becomes this. So we're just moving the mg term over to the other side. Notice here, they're both positive, or both plus signs, and then here we have a negative and a positive over here. Since these are both equal to t, then we can set them equal to each other. So I'm going to take this guy, put it here, and take this guy, put it here, and then we'll solve for a. So we'll just do some algebra solve for a, and we end up with an expression for a system like this, a very common situation we'll be in, where we can get the acceleration if we know the masses. Let's take an example here. If mass 1 is 80 kilograms and mass 2 is 100 kilograms, then we have 100 minus 80 divided by 100 plus 80 multiplied by g, and that gives us our acceleration. And I got 1.8, so you can check that. 1.08, so you can check that. Okay, so here's some situations where we have a out of equilibrium situation with tension. So a little bit more complicated. These are challenging problems because mainly because they're very typically going to be two equation, two unknown problems, as we saw with the example. And even as we saw here, we have two equations. Here we solve for one unknown. We could substitute this back now in for the tension if we needed to find the tension. Okay, I'm going to pause the video now, and then we're going to talk about one other situation where we use a pulley in a little bit more elaborate case. Okay, let's look at this crazy contraption here. We have a rope going straight down here with a mass M. We've got a pulley that's anchored to the wall. So this pulley's fixed like this, and the rope just skims this inside of this pulley. Now we have a freely moving pulley over here. So this is free to move. And right now we have it set so that it just skims the inside of the pulley on this side of the rope. And we're going to be able to pull, from this side. Now, we pull this and we start to pull, the rope will distort like this. And because the rope is a fixed length, this mass has to rise, right? So by pulling this sideways, this mass rises. But we're going to see that this more complicated setup is different than just pulling on that single pulley, on a single pulley like this. Because when we do that, then we have to pull with the same amount of force as the weight. When we do this, we have something called a mechanical advantage. We don't have to pull as much, at least initially, on the weight. So let's set this up, and I'm going to simplify this picture to just a drawing like this. And we've got this angle that this rope starts to make here. Here we have this angle. The angle is 90 degrees right here. So this angle, 90 degrees. If I start to pull this, it starts to become less than 90. And if we could imagine this being pulled way out, then eventually this difference would not be very much at all, and we would be 0 degrees. So in the limit that we could pull this all the way out to infinity, the angle would go down to 0. Okay, so that's try to see this picture sort of simplified this way. We have an angle here. We have the rope in this direction. We also have the rope in this direction. So there's a tension force pulling this way and a tension force pulling this way that we're overcoming with our pulling force this way. So our pulling force is this way. And so let's look at now some of the facts here about this situation, get ourselves oriented with it. Remember, the rope will just redirect the force, but the force is going to be the same all the time, and it's going to be mg, right? That's the only, we have to counter this weight. What kind of force does it take to just get that weight moving? So we have mg here, the tension here is mg all the way through here. So if we want to lift the weight, we have to overcome mg if we were to just pull straight up on the rope, if we just pull the rope straight up. Now, in this situation, this left situation, the y component of tension is the full weight, and the x component of tension is 0. So Tx is 0. But now in this situation, that's not the case, because we have an x component of tension, right? We have an x component of tension here. We have an x component of tension here. There is an x component, it's not just y. And that x component is mg cosine of this angle, just by SOHCAHTOA, and the y component then is mg sine of that angle. We've got two ropes, basically. We kind of think of this as two ropes, even though it's one rope. The rope is pulling this way and the rope is pulling this way. So we have a tension component here and a tension component here. So again, we have both of their magnitudes in this direction. So we're going to have a Tx over here and a Tx over here. So we will have to overcome a force of 2Tx. Now, let's think about that here. The Tx is cosine of theta. In this picture, theta is 90 degrees. So cosine of 90 is 0. It means that we need 0 force to just start to pull this, to lift this weight, to just start this weight. So we need actually 0 force to lift the weight. Now, as we start to pull it, our angle comes into play, and the force we need goes up. But for small deviations from 90 degrees, so if this was a very heavy weight and we just needed to lift it, say lift it off the ground so we could slide something underneath it, we don't need to pull this pulley very far. And if we don't pull the pulley very far, this angle is very small. And so it doesn't take much effort at all to lift an enormous amount of weight. And so that's it's called the mechanical advantage of this situation. And so where are we? Let's graph that. So if we're close to 90 degrees, then the force we need right here is very small. Okay, and then, oh, sorry, this should be 2, notice 2 mg. So if we start to pull this all the way out now, so this gets flat, then we come to smaller and smaller angles, and we actually have a mechanical disadvantage. I think I misspoke a little bit earlier in saying it's exactly like the single pulley case. It's not. We still have the tension from the 2 ropes, and as this starts to get the angle gets smaller and smaller and smaller, we rise in the amount of force needed to lift that weight. And as we look at the formula here, when we get to 0, of course that would be way out at infinity, then we actually have to pull twice the weight. All right, so this is this more elaborate setup of pulleys, and we can see how it's a little more complicated than simply moving the necessary force from one end of the rope to the other end of the rope. When you set up complicated systems like this, you get more complicated behavior. And we won't go any further on this, but in many physics books they have extra chapters on how to make all sorts of elaborate pulley systems. So if you're interested in that and learning a little bit more about mechanical advantage, then that's something you could look into.